In this video, we're going to learn how to find a basis for the row space of a matrix. Before we get to that, we need to understand how do elementary row operations affect the row space and null space of a matrix. And the theorem says that an elementary row operation on a matrix A does not change the row space and does not change the null space of A. As a side remark, they usually change the column space of A. So here's the proof. So there's three types of elementary row operations. The first is scaling a row by a non-zero scalar, and that does not change the row space of A. Remember, the row space of A is the linear combinations of rows of A, and so if you scale by a certain number, you're not going to change the possible linear combinations. Similarly, interchanging two rows obviously does not change the row space of A. What's slightly more difficult to see is that the last elementary row operation of replacing a row by adding to it a multiple of another row. So suppose we do that and let A prime be the resulting matrix. Then any linear combination of the rows of A primed, so that's going to be an element of the row space of A primed, will be, well, some scalar multiple of our new row K plus the linear combinations of the other rows of A primed, but that's the same as the rows of A because we didn't change the rows, these other rows besides RK. Okay, and then since RK primed, our new row in A primed is equal to the original row in A plus some scalar multiple of another row in A, we get that RK primed is equal to this, and then distributing the x to the k, which is a coefficient or a scalar constant, multiplying RK primed, we get this. And so what we see is that this linear combination over here is a linear combination of RK and some other rows of A. And therefore, since RK is a row of A, we have a linear combination of rows of A. So what we see is that if we start with any linear combination of rows of A primed, we get a linear combination of rows of A, and that's equivalent to saying that the row space of A primed is a subset of the row space of A. The proof of the converse direction is similar. So suppose, or what we do know is that RK primed is equal to RK plus A times some other row. And then solving for RK by subtracting A, RL from both sides, we get this. In other words, row K, our original row in our original matrix A, is equal to our new row K minus some number times a row L. So in any linear combination of rows of A, if an RK appears, it can be replaced with RK prime minus ARL. And so then we will get a linear combination of rows of A primed, because RK primed is a row of A primed, and RL is also a row of A primed, in addition to being a row of A. Okay, so we see that row space of A is a subset of the row space of A primed, and then combining these two inclusions, we get that the row space of A is equal to the row space of A primed. If this proof is a little hard to follow, don't worry too much about it. The take-home point is just that the elementary row operations do not change the row space of a matrix A. B of the theorem was saying that elementary row operations on A do not change the null space of A. So here's the proof. While an elementary row operation of A corresponds to multiplying on the left by an elementary matrix E, the new matrix, you start with A, the new matrix is E times A. And so, okay, let's say we had a vector in the null space of A. What that means is A times x is equal to 0. Let's multiply both sides by E. And E times 0 is 0, and therefore EA times x is 0. And so that means x is in the null space of EA. So the conclusion is if we start with a vector in the null space of A, we get a vector in the null space, or that vector is in the null space of EA, and so therefore the null space of A is a subset of the null space of EA. We're trying to show that these two null spaces are equal on the nose, and so let's go the opposite or converse direction. Let's start with a vector in the null space of EA, and so that means by definition of null space, EA times x is equal to 0. Now these elementary matrices are invertible, and so let's multiply both sides of this equation by E inverse, and we get that AX is 0, and so x is in the null space of A. So we get this inclusion here, and then combining this inclusion and this inclusion, we get that the null space of A is equal to the null space of E times A. And in words, that's saying an elementary row operation does not change the null space of a matrix. If we start with the matrix A, do an elementary row operation to get a new matrix EA, those two matrices have the same null space. Okay, let's finally do an example. Let A be a matrix, so here I've chosen a specific matrix, and the question is find a basis for the row space of A. So the solution is to just find the reduced row echelon form of A, and then the answer is that once you find that reduced row echelon form, take the non-zero rows in that reduced row echelon form of A, which I'm denoting A dot ref, which is the Sage math command for finding the reduced row echelon form of a matrix. So these non-zero rows will be a basis, I claim, for the row space of A. Again, these are the non-zero rows, not of A, but of the reduced row echelon form of A. Okay, now why is this the case? That's because these rows span the row space of A, since this fact we've just seen is that doing elementary row operations does not change the row space of a matrix. So if we start with the matrix A, do a bunch of elementary row operations to get to the reduced row echelon form, both of these matrices A and ARF will have the same row space. And then why are these non-zero rows linearly independent? Remember, we're trying to find a basis. A basis is something that spans and is linearly independent. The reason these rows are linearly independent follows from analyzing the position of the pivot ones. Let's see what I mean by that. So here I've asked Sage to do the reduced row echelon form of the above matrix A, and again, you can do this by hand, but by now you can just use Sage math. Okay, and so what the answer is saying is that take the non-zero row. So here there's the first row, the second row, and the third row. Those are going to be the answer to our question. In other words, those form a basis for the row space of A. Even though these rows are not rows of A, they're rows of the reduced row echelon form of A. Okay, so let's throw those rows into a list here. So here's just the command for what am I doing? I'm taking the rows 0, 1, and 2 in this example because these are the non-zero rows. Now, again, Sage starts counting at 0, so row 0, row 1, and row 2. Row 3 is all 0, so I don't want to include that. Also, remember how Python works in terms of range. Range from 0 to 3 starts at 0, but ends not at 3, but 1 less. So range 0 to 3 is the range 0, 1, 2, the numbers 0, 1, and 2. Okay, so this command here gives the ith row of a matrix. So here we're taking the ith row of this reduced row echelon form of A, and then we're turning it into a vector. Okay, so here are the 3 rows of A that are not of A, but of the reduced row echelon form of A that are non-zero. Okay, and then let's ask Sage if the list consisting of the rows give an answer to our question. In other words, do they form a basis of the row space? So again, a basis is something that spans and is linearly independent. So I ask span of L, is that equal to the row space of A? And Sage says it's true. And then I'm asking, are these vectors in L, are they linearly independent? Now, Sage has only a command, if I understand correctly, to ask, are they linearly dependent? And so let's ask, if they're linearly dependent, we need to tell Sage what vector space we're in. These are all vectors in Q7 or R7, since they have 7 components. And then we ask, are they linearly dependent? And Sage says it's false. They're not linearly dependent, which means they're linearly independent, which means, together with the fact that they span L, means that they form a basis for the row space of A, which is what we wanted to find. So to summarize, the answer is the non-zero rows of the reduced row echelon form of A. Next, I want to highlight a common error, is that the answer, we need to take the rows of the reduced row echelon form, not the rows of A. If we forget to take the rows of the reduced row echelon form, and instead, which is what I've done here, and that's why I'm calling it the list L wrong, is if I take the rows of A that are in the range, in this case 0 to 0, 1, 2, not including 3, then I'll get the wrong answer possibly, and in this case it is the wrong answer. So the rows of our original matrix that are in positions 0, 1, 2 are so, and then if I ask Sage, is the span of these 3 rows equal to the row space of A? And the answer is no. And then, so definitely this L wrong is not a basis for the row space of A. We can also ask, is it linearly independent, these 3 rows of A, the original matrix, not the reduced row echelon form of A? And it turns out that they're linearly dependent. Again, that's what we do not want. In fact, the way I cooked this example up was I took this first row and added to it twice this row to get, and made that the second row of my matrix. And so these vectors will not be linearly independent, and so therefore would not form a basis. So one can then ask, well, what about if we wanted to find a basis for the row space of A, but consisting of rows of A? So this is the same problem we just did, but now we're insisting on something more, that we want a basis consisting of the rows of A. And what we just saw was that if we just take the first 3 rows, that will not give us a basis for the row space of A. So there's a couple of ways to solve this problem. One is to use a built-in Sage Math command called a.pivotRows. And when I apply that to this matrix, it tells me 0, 1, and 3. Remembering Sage counts at 0, starts counting at 0. This means it's telling me, look at rows 0, 1, and 3. In other words, the first, second, and fourth row. Those rows will give an answer to this question of a basis for the row space consisting of rows of A as opposed to rows of the reduced row echelon form of A. Let's check that this gives the right answer. So let's make a list. I'm calling it R right because it's going to be the right answer as opposed to L wrong. Okay, so now I'm throwing in the rows of A, not the ref of A, but for the indices I that are in the pivot rows result. So 0, 1, and 3. That's what I is going to be. And so when I make that list, I get back row 0, that's this, row 1, that's this, and row 3, which is this. I'm omitting row 2. Why? Well, that's what Sage is telling me to omit. And then I ask, is the span of these vectors equal to the row space of A? And the answer is true, so that's good. And then are these vectors linearly dependent? And the answer is false, and that's also good. So these vectors span the row space and are linearly independent. Therefore, they form a basis for the row space. So again, to emphasize, this would be the answer to our question. Find a basis for the row space consisting of rows of A. Now, the second solution doesn't use the built-in command, which sort of hides the explanation for why or what is Sage doing. This solution is the following. So we use the fact that our process in a previous video of finding not the row space, but the column space of a matrix returns a basis consisting of actual columns of the original matrix, as opposed to columns of the RF of the matrix. In taking the transpose of a matrix, the rows and columns, or the rows become columns and vice versa. So the transpose is where you just flip the matrix. So we apply this procedure to find a basis of the column space of the transpose of A. So I had A above, and then if I let B be the transpose of A. So that just flips A. And now what was our procedure for finding the columns space, or finding a basis for the column space of a matrix? Well, that was quite simple. You just take the RF of the matrix. So we take RF of B, and then identify the pivot columns. So they're this, and this, the position of the leading ones. So the first column, the second column, and the fourth column. Or if you're numbering via Sage, it's column 0, column 1, and column 3. You can also ask Sage to take the pivots, and it will give you back the column numbers. Okay, and that's what we've seen that gives the correct answer. We've seen that the columns 0, 1, and 3 of B will correspond to rows 0, 1, and 3 of A, since the columns of B are the same as the rows of A. Anyway, to recap or summarize, the procedure to find a basis for the row space of A that consists of some rows of A are to take the matrix A, take its transpose. So then the rows turn into columns. Take the reduced row echelon form of the columns, then identify the pivot columns, and then use those indices to figure out or associate the corresponding rows of the original matrix A, in this case row 0, row 1, and row 3 of A, and that will be the A basis for the row space of A.